Hi guys, myself Pranav is here to deliver today's presentation, Power Transformer Part 47. As the subject is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with apparent power, a comprehensive review. Apparent power, VA, is the vector summation of active power, that is watts, reactive power, var, and harmonic power. It is also VA. Out of which active power means the effective power. Reactive power is the power which is stored or released by the inductors and capacitors. The reactive power, though, is not converted into useful energy, but has the influence to act as a phase displacement between the current and voltage waveforms. Harmonic power is the power which lost to harmonic distortion. Reactive power may be of inductive, capacitive, and harmonic reactive power, or a combination of all these three. That is inductive, capacitive, and harmonic reactive power. The presence of harmonics in electrical system would have to distort the current and voltage waveforms, that is to be deviated from sinusoidal waveforms. Harmonic currents, which are caused by nonlinear loads connected to the distribution system, would have to circulate in the system networks. The frequency of that subsequent circulating current might be on an integer multiple of the supply frequency. Nonlinear load such as variable speed drives, capacitors, arc furnaces, etc., when draws current that does not have the same waveform as the supply voltage, while that current flows through the system impedances, in turn creates voltage harmonics which distort the supply voltage. Now, impact of harmonic load. Harmonic power would have to create multiple number of undesirable consequences such as overheating of transformers, cables, motors, generators, and capacitors connected to the same power network with the devices which are responsible to generate the harmonics. Harmonics in the system network is rather be unavoidable and have a great impact on changing the power quality, which leads to endanger the connected equipment. Capacitors, if connected, are particularly much more sensitive to harmonic currents since their impedance decreases proportionately to the order of the harmonic present. Again, I repeat, capacitors, if connected, are particularly much more sensitive to harmonic currents since their impedance decreases proportionally to the order of the harmonics present. Harmonic currents would have to circulate having with higher frequency, which is an integer multiple of the supply frequency. We have already learned from the previous chapters. Now, effect of harmonics on power factor. Power factor does indicate that amount of electricity consumed by a specific load to produce work. With the introduction of higher power factor for a given voltage and current, there will be the more work to produce. Because of harmonics, as generated by nonlinear loads, the power factor analysis of a power system would have become increasingly complex. Power factor is, however, always be measured by the ratio between the real power in kilowatt and apparent power in kVA. Apparent power is the vector summation of the reactive power in kVAR and the real power in kilowatt. For linear loads that are to be indicated as resistive, inductive, or capacitive, real power component, that is work producing component, is P equals to kilowatt. See the diagram. Reactive power component, that is non-workable producing, Q equals to kVAR. Apparent power, S equals to kVA. Now, apparent power is the vector sum of the reactive power Q and real power P. Power factor equals to the cos phi, that is power factor equals to P by S, that is kilowatt by kVA. S equals to root over P square plus Q square, that is kVA equals to kilowatt root over kilowatt square plus kVAR square. From figure 157, it can be concluded a conventional power factor equation is absolutely for linear circuits. B, circuits may include some reactance which can create a phase shift between voltage and current, as well as creates a difference between the real and apparent power delivered to a circuit. C, real power is always be affected by the power factor of the circuit or load. Apparent power is independent of the circuit power factor. These four criteria are much important. When the load is purely resistive, then the current which has to be drawn will be in phase with the voltage and must have the unity power factor. As of the inductive load, the drawn current will be in lagging with the voltage and must have the lagging power factor. In case of capacitive load, the drawn current will be in leading with the voltage and must have the leading power factor. It can therefore be concluded that if the net reactance of the system is inductive, then there will be a lagging power factor, and if it is capacitive, then there will be a leading power factor. It is also to be noted that the current draw by all types of linear loads would always maintain a linear relationship with the applied voltage. But for the reactive load is concerned, it stores energy that has to release during a different part of the cycle. Reactive load is mostly used by the electrical equipment that include electromagnetic devices or depend on magnetically coupled windings where some degree of reactive current is required to create magnetic flux. Transformers, reactors, motors, etc. are the most common items to absorb reactive power, that is reactive current rather, for producing required magnetic flux. Reactive load also has to supply as the reactive losses on overhead power transmission line. While to discuss regarding effect of harmonics on power factor, it is of much necessary to have a clear conception of three forms of power factor, which are as follows. 1, displacement power factor. Number 2, distortion power factor. Number 3, true power factor. Displacement power factor. Displacement power factor is the fundamental power factor and can be defined as the power factor which is due to the phase shift between voltage and current of a linear load at the fundamental line frequency. In this case, there would not have any deviation from the typical sinusoidal variations in voltages and currents. Displacement power factor is thus to be indicated by the cosine of phase angle between the fundamental sine waves of current and voltage. This is a fundamental power factor which can only to relate with fundamental frequency, that is 50 Hz, and does not have any interference of harmonic currents. This value is much effective during the selection of capacitor bank for power factor correction. See the figure 158, voltage and current, sinusoidal form. Number 2, distortion power factor. The distortion power factor that has to depend on the total harmonic distortion caused by the nonlinear loads present in the system. Nonlinear loads have to draw currents in abrupt short pulses. The currents waveforms are thus to be distorted by these short pulses and can be broken down into harmonic components. Nonlinear loads would have been the main source of harmonics, which increases total harmonic distortion in the system network. Total harmonic distortion, that is THD, is the amount of harmonics on a system network compared to the network of the fundamental frequency, that is 50 Hz. By analyzing distortion power factor, it can have to measure of how much the harmonic distortion of a load current decreases the average power transferred to the load. Total harmonic distortion is thereby to analyze the total deviation of voltage or current waveform from ideal sinusoidal shape. Mathematical expression of distortion power factor in terms of total harmonic distortion is as follows. Distortion power factor equals to 1 by root over 1 plus THD square. It is thus to be concluded that higher be the total harmonic distortion, lower will be distortion power factor. Total harmonic distortion in nonlinear circuits would obviously have a close relation with the distortion power factor. In nonlinear loads, the acceptable distortion limit that would have to be properly quantified by applying the distortion power factor as an useful metric. True power factor. When the system is configured with both linear and nonlinear loads, then the power factor relationship would have become three-dimensional with the combined effect of the underneath power components. One is the real power, another is the reactive power, and number C is the distortion reactive power due to harmonics. That is P, Q, and H. Due to presence of harmonic component in apparent power in kVA, true power factor is also referred as the combined effect of displacement power factor and distortion power factor. That is represented as harmonic power factor, that is HPF. Displacement power factor is the cosine of phase angle between the current and voltage fundamental sine waves. This functional power factor is only referred to the 50 Hz sine wave and would not consider actual effect of harmonic currents. That is excluded from harmonic currents. However, displacement power factor can either be leading or lagging. But in case of distortion power factor, it is neither leading nor lagging. True power factor is the overall power factor of an electrical network, which depends not only on the displacement power factor, but also depends on the distortion power factor, that is HPF, harmonic power factor at that network. True power factor, therefore, is the displacement power factor into distortion power factor or harmonic power factor. Now, true power factor equals to cos phi into 1 by root over 1 plus THD square, total harmonic distortion square. From the expression, it is thus to be concluded that the true power factor must have to be deteriorated with an increase in harmonic distortion in the network. Again, I repeat, from this expression, true power factor expression, it is thus to be concluded that the true power factor must have to be deteriorated with an increase in harmonic distortion in the network. Effects of harmonics on capacitors. As of the load characteristics of the electrical network, the power factors are usually referred to leading or lagging. For capacitive load, that is reactive load, the power factor is always being leading since the current leads the supply voltage. For inductive load, the power factor is always being lagging since the current lags the supply voltage. An inductive load is a type of electrical load through which the current, when starts to flow, then a magnetic field would have been rather created and then stores energy. That energy is reactive power. Inductive load that has to consume reactive power, which is rather not been converted to useful work. With the induction of reactive power into an electrical network would thus to instigate a decrease in overall power factor of that network circuit. As of the basic concept, it has been concluded that the power factor and the load current are inversely proportional to each other. However, the resultant effects as due to occurrence of low power factor are stated below. An increase in current will increase the copper losses in the transformer, transmission line, and connected load. Number two, a large line current as drawn that tends to have a voltage drop in the generator, transformer, and transmission network. Number three, on the perspective of a poor voltage regulation, an extra cost may have to be incurred on implementing system voltage regulator. Number four, large amount of current which would have to carry that obviously intends to have a provision of transmission conductor with larger cross-sectional area. As that is material cost will be much more. As the kVA rating of the equipment is inversely proportional to the power factor, so lower be the power factor, then higher would be the kVA rating of the equipment to achieve the same kilowatt output. Inductive loads such as induction generators, induction motors, power transformers, arc furnaces, etc., have therefore to require reactive power for their magnetization. If the reactive power is consumed from the power grid, then an occurrence of voltage dip must have been the resultant effect. Such type of linear loads are drawing large current which is lagging the source voltage. Inrush currents are the most significant cause of voltage dip, which also referred to as voltage sag. This voltage dip may have a variety of consequences as related to sensitive equipment such as PLCs, that is programmable logic controllers, variable frequency drives, VFD, and contactors which are connected to that grid. It is therefore to conclude that wide variations in reactive power flow in grid system would have been the prime concern for the basic occurrence of low power factor as well as voltage dip phenomena. Hence, the reactive power which are being consumed from the grid by the operating inductive loads would thereby necessary to compensate. To improve the displacement power factor of electrical power system, it is an usual practice to insert capacitor banks in the network. However, if the connected capacitor bank would have to supply reactive power more than the requirement of the grid, then there will be an occurrence of voltage swell, that is voltage over voltage, which again affects the operating performance of sensitive loads. So, in accordance with the load pattern as well as the behavioral characteristics of the grid system, these capacitor banks are made to switch in and out of the network circuit accordingly. In the present industrial arena, nonlinear loads such as static power converters are the most significant devices used for a variety of purposes. A load which is indicated to be nonlinear if its impedance changes with the applied voltage. Again, I repeat, a load which is indicated to be a nonlinear one if its impedance changes with the applied voltage. Changing of impedance, that has to signify that the current as being drawn by the nonlinear load will be of non-sinusoidal type, even if the subject load is connected to a sinusoidal voltage. So, it can be concluded that the impedance of nonlinear load would have to vary throughout the cycle of input AC voltage waveform. Most important, it can be concluded that the impedance of nonlinear load would have to vary throughout the cycle of input AC voltage waveform. Nonlinear loads, when draw currents in abrupt short pulses which contain harmonic currents, may have to impose a distorted voltage waveform. Nonlinear load draws current through system, and whenever the load creates current distortion, that will cause voltage distortion. These harmonic currents that would start to interact with the impedance of the power distribution system, and for which have to create voltage distortion also. Not the current distortion, but occurrence of voltage distortion would only be the prime factor to affect the operational characteristics of the associated power distribution system equipment as well as loads connected to it. In an industrial environment where there is considerable presence of nonlinear load with having high distortion reactive power component, because of harmonics would be the most indicative cause for low power factor on a power system. Power factor is the ratio of work producing real power component, that is kilowatt, to apparent power component kVA, that is power factor equals to kilowatt by kVA. In this case, apparent power component, that is kVA, is compiled with harmonic components. True power factor is the combined effect of displacement power factor and distortion power factor, as due to have total harmonic distortion. True power factor is actually expressed as the product of displacement power factor, that is PFD, and distortion power factor, DPF, that is true power factor equals to PFT equals to PFD into DPF. For most typical nonlinear loads, the displacement power factor will be of near unity, but because of distortion component, as introduced by the harmonics, the true power factor will be significantly low. Analytically, the poor power factor as caused by nonlinear loads would thus have to be improved only by removing the harmonic current components. True power factor can thus be improved in a following manner: increment of displacement power factor by installing a capacitor bank across the supply source. Number B, to mitigate harmonic distortion by implementing different types of harmonic filters such as passive, active, hybrid filters, etc., which leads to improve the distortion power factor. Designing harmonic filter in capacitor bank is also being the prior option to improve the displacement and distortion power factors. Let's stop here. Further to be continued at later stage. Thank you. Thank you for listening the video. Kindly do like, share, and subscribe. Your subscription would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section, please. Thank you. Thank you for patient hearing.